Alright, so we're going to continue our discussion about radicals, and we're going to talk about adding and subtracting. So this is going to be very similar to when we talked about adding and subtracting polynomials. Now the first thing we have to do is, before we even consider adding and subtracting radicals, we need to simplify them first. So we have to get those exponents as simplified as we can, breaking them up into their perfect squares, yada, yada, yada. Once we do that, though, and we have all the terms simplified as much as they can, then we're going to be able to add them or subtract them. And we can only add them or subtract if they are like radicals. So this is actually very similar to the whole concept with the polynomials. Remember, you can only add polynomials together if the variables like x and y were the same. So if you have an x squared and another term that has an x squared, you can add them together. And you can only add x's and x's together. So for example, here, if we had something that looked like this, we'd have to take these two terms and simplify them into their simplified forms. This can be rewritten as x to the 6 times x. So when you take the square root of x to the 6, you get x cubed. This one would also be the same thing, except we also have this 4 in front. So we know that we can square root that because that's a perfect square. So this one actually simplifies to 2x cubed times radical x. Since the term and the exponents are all the same, then we end up, we can add the two coefficients. So this is a 1 and that's a 2. Gives us 3x cubed radical x. And that's pretty much it. So we're going to do 4 practice problems, 2 from the guided practice and 2 from the independent. So here's the first set. Pause the video, work itself, and we'll go over in a second. All right, so with this, we're going to rewrite these two in their common terms. Now, because of the fact that they're going to need to have the same final radicals, what we're going to actually try to do is find numbers that can go into both of these. So for example, this one, I can already tell that this one is divisible by 25. So I can rewrite 75 as 3 times 25. And because of this, because I know that 3 is going to be left over under the radical, I know this should also be divisible by 3. So when I plug this into the calculator and I do 192 divided by 3, I see that the remainder would be a perfect square, so this is 3 times 64. So this expression will turn into this. 3 times 25, and then the variables actually don't change because a is a perfect square and b can't be simplified anymore. And then the 92 is 3 times 64. So I simplify every perfect square. 25 and a to the 4th becomes 5a squared. And then I'm left with the 3b underneath the radical. Same thing here. 64 and a to the 4th are the perfect squares. So we get a 8 a squared. And then once again left with radical 3b. From here, now I'm just looking at the coefficients. The a squared radical 3b is the same. So I'm going to look at the 5 and I'm going to look at the minus 8. So 5 minus 8 is negative 3. So my final answer is going to be negative 3a squared radical 3b. And that's pretty much it. Down here, there's another term, but it's not that much more difficult. Again, we try to find perfect squares that will go into these. 28 can be rewritten as 4 times 7. This one's also divisible by 7, and this can be rewritten as 7 times 9, and 112 can be written as 7 times 16. Again, the a to the 4th is a perfect square, so I don't have to touch it. Simplify this one extra step. So the 4 is the perfect square, so that gets pulled out and is multiplied by this number in front. So I get the 2 from before times another 2. Then we get the a squared. Radical 7 is left over. This one, the square root of 9 is 3, so we have 3a squared radical 7. And then the 16 is the perfect square. Square root of that is 4, so I get 3 times 4, a squared times radical 7. Combining all this together, this is 4 plus 3 minus 12. So if you plug into your calculator 4 plus 3 minus 12, we end up getting negative 5a squared radical 7. All right. Now these are the independent questions, so pause the video, work stuff, and we'll go over in a second. All right. So taking the 32 and the 18, rewriting them. 32 can be rewritten as 2 times 16, and 18 can be rewritten as 2 times 9. So taking that one step further and trying to simplify it, we get 2 times 4x times radical 2 minus 3 times 3x times radical 2. 2 times 4 is 8, and 3 times 3 is 9. So 8 minus 9 gives me negative x radical 2. All right, so for this very last question, what we're going to do is same thing, pretty basic. This one, the only one that can be broken up is the b to the 5th. Can be rewritten as b to the 4 times b. This one, I'm going to rewrite as 4 times 3. So my expression will now look like this. A squared and b to the 4th are perfect squares, so this I can rewrite as a times b squared. This one, 4, is also part of that. Square root of 4 is 2. So my expression becomes ab squared times radical 3b plus 2ab squared times radical 3b. Again, we have a 1 here and a 2 here. So adding those two numbers, I get 3ab squared radical 3b. And that's pretty much it for these. Again, it's playing with the whole idea of being able to simplify the expressions and then making sure that you have like terms before we can add and subtract. The only difference is now when we talk about like terms, instead of just looking at the variables, we also have to look at the radicals and make sure that those radicals are exactly the same. So this time, I believe most of them were probably all going to have the same final radicals. But when we return to this later on, you'll see that we'll probably change that up a bit. All right, once again, answer the rest of the questions and just submit that in the next day. And make sure that if you have any questions, you contact me as soon as you can. You can message me on Remind. Anything else, good luck. Have a great day.